Hello everyone. In this video, I will demonstrate how to perform data screening when dealing with multivariate statistical analysis techniques using ungrouped data, which is typically the case when you're dealing with multiple regression or factor analysis as such. So this is my third part of the video. In the first and second part, we went through all these points here, the reasons you would like to perform data screening prior to conducting any statistical analysis. And there are at least four reasons. The quality of the data matters. The garbage in is going to be your garbage out. You need to make sure that your data is of high quality. Then you have to deal with the missing values. If the missing values are less than 5%, then the most typically used option is to delete those cases from the analysis, and that's what we're going to focus on here. If the missing values are somewhere between 5% to 15%, then we usually go with the data imputation. In case of numeric variable, we do the mean substitution. And in case of categorical variables, we often go with the mode substitution. I discussed these things pretty much in detail in part one and part two, but here we just want to give you a brief overview. So basically, we're going to start with outliers. So outlier analysis needs to be done at univariate as well as multivariate level. Now, since we are talking about multiple variables here, even though this is advanced univariate analysis, multivariate outlier analysis will come into the picture. And it's always good to perform multivariate outlier analysis because univariate outlier analysis does not guarantee that you're going to satisfy the multivariate outlier analysis, which is rather more important when you're dealing with multiple variables that are acting together. So once we deal with the outlier, we're going to start talking about the assumptions that we are supposed to meet to perform any kind of statistical technique using ungrouped data, such as multiple regression. We're going to talk about normality, linearity, and homoscedasticity. So let's talk about the example. Again, I'm referring to this book here, very good book. So if you're interested, please go through this book. Suppose that we are interested in investigating the degree to which the variables of years of education, age, and hours worked weekly predict in income levels. So this is a typical linear multiple regression we are talking about here. So we have one outcome variable that's being predicted by our three predictors here. So education, age, and hours worked per week. So this income variable is a transformed variable from the original one, and I discussed that transformation in part one. So if those are interested, please go ahead and look for part one of the video here. But we're going to start with outlier analysis here. So with that, I'm going to switch back to SPSS. I'm going to go to the variable view. Accuracy of the data is already been taken care of by categorizing those values which are not applicable as missing. So age might have some values, 98, 99. Obviously, they cannot be the age. So we're going to categorize them as missing values, right? So anything that is 0, 98, or 99 will be categorized as missing. Education also has some non-qualified entries, 97, 98, 99, and we don't want to get confused about that. So if you leave this thing there in the analysis, SPSS will not know whether these values are applicable or not. It's just going to assume that they are valid entries and perform the analysis, and you'll get the output. But that output will not be sort of valid or accurate. So that's where this data quality or accuracy comes into the picture. So likewise, you have hours worked. It has some inconsistent values as well. So that they are taken care of by categorizing as missing as well. And our income 4 is basically a transformed variable, transformed from our income 91. And if you see our income 91, it has some non-eligible values, 22, 98, 99. These are not eligible, or I would say not applicable, and 0. So all those are been taken care of by categorizing as missing. Okay, so we should have done 22 as well, and that's where you have to go through my video 1. I showed you there how to do it. So once you have taken care of this one, as I said, multivariate outlier analysis is rather more important than univariate outlier analysis. So we're going to start doing that. And when you are dealing with metric or interval scale variable, the way you do outlier analysis is using Mahalanobis distance. So that's the first thing we're going to do here. We're going to calculate the Mahalanobis distance here. So we'll go to analyze regression, linear regression here. Our dependent variable in this case is going to be ID, because this procedure is not affected by a dependent variable. We are not predicting anything here. We are just trying to find out the Mahalanobis distance here. And our independent variable are I would say age, education, hours worked, and we will put all of them there, including dependent and independent variable. So our income is basically our dependent variable, but we are kind of calculating the Mahalanobis distance here. Now what it does is, is going to take these 4 variables and go through the entire data set and sort of find a global centroid. And from there, it's going to see how far away each record is, or each case is. And if the case is farther away or extreme, it will be categorized as outlier. So we're not interested in any statistical analysis here. I'm just going to uncheck this one. We're not going to do any plots. Save, we want to save Mahalanobis distance here, so make sure that is checked here. Options, exclude case list-wise. So if any case has a missing value or any part of the case has a missing value, that complete case will be ignored. So only cases that have all the values will be included in the analysis. So we're going to do that here. And that's it. And so I'm going to go say okay here. So it's going to go ahead and do the analysis here. So if you see, it has calculated the Mahalanobis distance here. It tells you the maximum value and the minimum value here. Okay. So we're going to see that which we don't know which one is critical. We're going to find that one out here. If you go to the data set here, you see it had added one more column here with the calculation. Okay, so what I'm going to do here, I'm going to delete this one because we have to redo it anyway. So we have this Mahalanobis distance here. I'm going to find out the critical values. So I'm going to go to data, transform, compute value. I'm going to say probability of Mahalanobis distance. You can give any name that you want. So I'm going to say 1 minus cumulative density function of chi-square here, and we're going to pass on the Mahalanobis distance, basically, which is basically the chi-squared distance or chi-squared value here, and the degree of freedom is simply the number of variables we are using, which are 4. So I'm going to say okay here. So it's going to go ahead and create another column with the probability value. So these values are a case is considered outlier if the probability values falls below 0.001. And the best way to do that is we use data select cases. I'm going to say if condition. I'm going to say select only those cases where this value is greater than 0.001. So if it is less than 0.001, or equal to 0.001, that case is considered outlier. Okay, so continue this one and say okay here. If you go back to your data here, that's I'm gonna sort this descending, or maybe ascending. Okay, or maybe this one, Mahalanobis distance, we can do descending. So if you sort this descending, is going to give the critical values at the top here. So these four are considered outlier, because if you click on those values, they are less than 0.001. So filter is on, so this will be ignored going forward. Okay, so we need to make sure that this is how you do the outlier analysis. Now, once we are done with the outlier analysis, next thing we have to start checking the assumptions of normality, linearity, and homoscedasticity. Now, this has to be done both at univariate level and multivariate level. So let's start with the univariate level. I'm going to go to analysis, descriptive statistics, explore. I'm going to put all those four variables there, which are already here. But if not, you put it there. Statistical analysis, we're not gonna do any outlier analysis here, which we already did it. I'm gonna display both plots and this thing. The plot, I'm more interested in histogram rather than stem and leaf chart. Box plot is gonna produce it, and we can also do the normality plots with test here. So continue that one. Say okay here. So basically, if you just look at the histogram of each variable, it gives you some idea about the normality. For example, the age looks like it's a little bit positively skewed, but education is fairly normal, although it has some high peaked values there. And histogram also looks pretty normal, some high peaked values here. Our income for is already transformed, so it looks pretty normal. So what we're gonna do is, for the age, we're gonna transform that and take the square root and create another variable to take care of this moderate positive skewness. Box plot is gonna show you some outliers, but these are all at univariate level. Okay, we are not worried about the univariate outliers anymore, because we are doing sort of multivariate outlier analysis. Although this is not multivariate technique, this is more kind of advanced univariate technique, but we have to consider the multivariate outlier. Univariate outlier, if you take care of them, it does not guarantee that you are taking care of the multivariate outlier analysis as well. Multivariate outlier analysis is far more important to satisfy, because all these four variables are going to be sort of acting together. So we are more interested in combined effect rather than individual variable effect. So we're going to ignore this one. Okay. QQ plot also you can see it, but basically they're going to convey the same information as the histogram. So we're going to do that. Let's go ahead and create another variable. I'm going to say age2, and that should be, I'm going to say arithmetic function. Let's say I'm going to square root of age. So this is going to go ahead and create a variable for us, right? age2, okay, which is transformed. And now if you again do the statistical analysis with all those variables, except what we're going to do is we're going to bring age2 now. Say okay here. And let's say the age2 histogram, now it's pretty normal, way more normal than what it should be. And test of normality, the KS test, or Kolmogorov, Smirnov, and Shapiro-Wilks test, they're all showing significant results, which means that we reject the null hypothesis, which means that the data is not normally distributed. So if the data is not normally distributed, basically we have to do more transformation. But you need to understand one thing, that these tests of normality, they are highly sensitive to the sample size. So if the sample size is big enough, or for any large sample sizes, this test will always produce significant results. So we should always do a visually analysis, and looking at the histogram or QQ plot, we are very confident that although data may not be perfectly normal, it's very much near normal, and we can go ahead and perform the analysis. And again, these are all looking at univariate analysis. We need to be doing multivariate analysis, because these might not affect the analysis as much, because we are more interested in combined effect of all the variables. So what we're gonna do now is we gonna do the multivariate normality plots, and the only way to do that is graphically is use the scatter plot. By doing the scatter plot, we can test the bivariate normality and the linearity as well. So we're gonna do that to graphs, legacy dialogues, scatter plot, define. I'm gonna say education, hours worked, income, and age 2. Okay, I'm not gonna do anything. I'm not going to do anything here. Exclude cases list-wise. So any case that has any missing value will be excluded from the analysis here. Say okay here. So it's going to give you this nice looking scatter plot. Now, if the data is bivariate, normal, and linear, you should be looking for an elliptical shape. Okay, elliptical shape here. But here we don't see any elliptical shape as such. We see more kind of a rectangular pattern. So this basically tells you that we are not satisfying linearity and normality assumptions. But just looking at it, you don't see any non-linear pattern as such. They are very symmetric, very uniform distribution. So I guess I'm very confident moving on further with the analysis as such. If the scatter plot doesn't look elliptical, or you're not satisfied with the visual analysis, and you see that data looks not normal or not linear, then you might need to go for additional transformation, or you can use this variable for multivariate analysis, or combining them together to perform the analysis. You might decide to do only univariate level analysis. But again, these are very subjective. Scatter plots are very subjective, very judgmental, and we need to be adopting more advanced analysis for residuals. For these assumptions. And one of the way you do that is doing the residual plots using the predicted values in multiple regression. Now, the residual plots are considered very robust. And basically, you can check all the assumptions of normality, linearity, and heteroscedasticity in one simple plot. So we're going to do that here. So the way to do that is go to Analyze, Regression, Linear Regression here. Our dependent variable this time is our income 4, so I'm going to bring our income 4 here, and age 2 is dependent variable. So basically we are performing multiple regression, okay, but we're not interested in any coefficient as such. We are more interested in just the residual plots. We're not going to save any Mahalanobis distance here. Well, we're not interested in that. I'll go to the plot. These are my residuals which go on the y-axis, and these are my predicted value for my dependent variable that goes on x-axis. Okay, I'm going to continue that. Options is going to exclude cases list-wise again. So we're going to say okay here, and it's going to produce this nice looking scatter plot where on the x-axis you have predicted values, and on the y-axis you have residuals, standardized format. Now, how to interpret this plot? Basically, what you should be looking for if you are if you need to meet the assumptions of normality, linearity, and heteroscedasticity, you should be looking for sort of a rectangular distribution of the data, where most of the scores should be concentrated around the center line or near the zero. Okay. If the data is not normal, basically what you're going to do is basically what you would see is most of the scores are concentrated above the zero line or below the zero line, but they will be very uniform. And if the data is not linear, then you're going to see non-linear pattern. Okay, maybe a curvilinear orientation of all these scores. And if the data is heteroscedastic, then you're going to see most of the scores are concentrated on either the left side or the right side, or you're going to see some sort of increasing in the residuals pattern. Okay, so I can quickly show you the graph here. If you just go and Google it here, let's say residual plot patterns for regression. I'm going to go to the images here straight, and you see that. So this is like more kind of a non-linear pattern. If you have residual plot showing this kind of pattern, you cannot use linear multiple regression. You have to use regression which is more suitable for non-linear patterns, right? If you have a plot like this is more kind of showing you there is a time dependency here, maybe. This is the ideal plot you're looking for. Very nice rectangular pattern with residual scattered all along. This is very much like a heteroscedasticity, because these two plot tells you that as you go on the right side here, the residual values are increasing, or the errors are increasing in your prediction. So this is very much heteroscedastic. Okay, and non-linear, non-normal, basically what you're going to see is most of the data points are just falling above the line or below the line, but they are very much like a rectangular fashion. This is something you have to keep in mind when you're doing the analysis. Here, we don't see any non-linear or not normal, and data is nicely, all the scores or residual scores or standardized residual scores are centered around the zero line. So I think I'm satisfied, and as I'm going to assume that we are satisfying that normality, linearity, and heteroscedasticity assumption. So this is how you perform the data screening and examination when you are basically dealing with the ungrouped data such as multiple regression. With this, I'm going to stop my video here. Thank you very much for listening.